this as sigma of x times 1 minus sigma of x, or sigma of x times sigma of minus x. So it makes evaluating this derivative easier. Okay. So, I don't know, would you like to copy this? Because I see some of this will take me notes. Okay. And this is just a table that I made for myself to summarize all the models that are discussed in the lecture. Yeah, more or less the same things that we talked about. Just ordered in a table, actually. So what you see here is the linear part is always the same. And here you have a bunch of functions that go with specific types of distributions, which model y given x. And here you have the inverses of the living function. And when you choose which model depends on how you're modeling. So if you have binary labels, the linear model is probably not the way to go. For example, it derives from the context which model is the appropriate one. But anyways. In an exam situation, like the range of x and y can be a hint at which model is the right one. For example, if you're regressing binary labels to some scalar covariates, you'll probably better off using logistic regression. If your dependent variable is some sort of count, maybe Poisson is the way to go. I don't know. Pay attention to the ranges of x and y. Okay, with that, let's get started with the first exercise. So task A is just about logistic regression. Here you have the formulas for logistic regression, and your task is deriving a decision boundary. What is a decision boundary? Let's say your data is on the XY plane with different labels, and you're trying to find a line like this that best separates your data. So on one side, there's one label, and on the other side, the other label. And this is your decision boundary. And in case of binary labels, this is how we can, not all binary, but this equation characterizes such a decision boundary. Because along this line, your model will output the same probability for both classes, or it will not. Okay, so that's task A. And in task B, we have the additional information that your data looks something more like this. So in this case, you can say by just visual inspection that you won't be able to find a line that perfectly separates your classes, your labels. But what you can see is there is an elliptic curve like this that does separate both classes. And here you have the ellipsoid equation. And you're supposed to use that to reformulate your decision boundary and redefine your model with that new decision boundary. That's task B. And then we'll implement this in Python. But I would give you about 5 minutes for tasks A and B, because this is a longer exercise. You just try to solve them conceptually. You don't have to finish it. Just, yeah. Until the 30 minutes. And you can always ask questions. P here stands for the probability of outputting label 1. So here's P. And yeah, we want to find out a function description that has this shape from this equality. So we have just the options y equals 0 and y equals 1. That means, first of all, so that means how can I write probability y equals 0 as a function of the thing on the left? So
1 minus.
exactly. Thank you. So they have to sum up to 1. Otherwise, we don't have a well-defined probability measure. So on left we have p. On the right we have 1 minus p. And we can solve for p to get p equals 1/2. And here we do have an so what do we need to use to obtain an expression that depends on x1 and x2? We have this thing, right, that relates p to our linear model. So we will use that, and I will shorten this to eta of x instead of dragging it along. So I substitute for p e to the power of eta of x over 1 plus e to the power of eta of x equals 1/2. And then we solve for e to the power of eta of x, right? And then we can apply the natural logarithm to both sides. It's a monotonic function, so we don't have to pay special attention to this relation here. And we end up with this equation. Eta of x equals 0. And then we can substitute back the definition of eta, which was eta 0 plus eta 1 x1 plus eta 2 x2 equals 0. And we wanted an expression for x2 that depends on x1. So we just solve for x2. And define the right hand side as our f of x1. Right? So that concludes part A. So what we did essentially is, for example, just substitute plus 1 for all equations, and you get 1 minus x1. And if you draw it, it will be a line like this. And it is a decision boundary, it's not a linear model. So we're still doing logistic regression. So here you will say, you'll output the prediction plus 0, and the other side plus 1. For example. So you have a relationship that goes like this. P larger than 1 minus b translates to x2 larger than f of x1, and vice versa. prediction will be +1 if eta of x is larger than 0. These are all equivalent formulations of your decision criterion. So this is one way to write it. Are there any questions on this? Okay, then let's do task B. Now, we plot the data and we notice that the actual decision boundary must have this elliptic or circular shape. And this is how we can specify the points on this circle or ellipsoid. So, and specifically we have a majority class 0 population within the circle and class 1 population outside of the circle. So we can formulate our decision criterion as if right? I can say this by just looking at how my data points are distributed. And conversely, we have mostly class 1 outside of the circle. Now, the definition of a decision boundary stays the same. And here we derived some characterizations of say decision point, decision boundary. So the idea is still try to fit a logistic regression model to this balance, but we just have a problem that the decision boundary just isn't linear. But it still makes sense to fit a logistic regression model because we have binary labels and scalars that are covariates. So what will be your first idea here? So we're still trying to fit a logistic regression model. So how can I linearize this? It's very simple, but I'd like you to answer this.
Using log?
Not necessarily. Maybe look at the information that's given here. So in the dataset itself, there are columns that contain quadratic terms that contain x1 squared and x2 squared. So,
Substitution?
exactly. So we can regress on the quadratic terms themselves instead of x1 and x2, right? So this was my decision criterion. So what can I do? We'll substitute on quadratic terms directly. squared minus r squared. And actually this substitution isn't even necessary. I'm just trying to write everything more tidily because eta only needs to be linear, and actually it does make sense because this is not linear regression. But I mean, it actually suffices that eta of x is linear in your coefficient. So the actual substitution we need to do is with regards to the parameters. Okay, so if this is my decision criterion for class 1, my decision boundary looks like this, right? And I'll make it. So this is my decision boundary. And now we'll just substitute again. So the idea is, okay, your data and the decision boundary may not be linear, but you can find some coordinate system. For example, you just project your data to certain polar coordinates, for example, and all of a sudden you do have a decision, linear decision boundary. So that's the idea here, I believe. And just you can use this new decision boundary that we define here to fit the logistic regression model. Okay. See, there are more things to mention. No. Okay. That would be. Yeah, first off, of the first exercise. I'm aware that you're spending longer on this first one, but and out of this tutorial sheet, I think it's the most important one. Okay, are there any questions? Yes, I'd like you to try to fit a model to this data using Python. Yeah, there's a template on Moodle. Sorry, this is but yeah, task D is it's asking the question, and yes, the question is data logistic regression gives you automatically the optimal number of correctly classified numbers. And we'll talk about them in some detail. So again, I've saved 5 minutes working time. I'm going to see you. Mhm. Yeah, sure. I mean, so exactly, maybe, yeah, you're right. I mean, the idea is you can use the argument of the probability for, I mean, 1/2 and use, that's perfect. Good. Okay, let's discuss the solution. Yeah, here are all the necessary imports. At this point, I'm assuming all of you have a working environment with these libraries installed. Yeah, first step is, like always, read from this CSV into a pandas data frame. Have a look at what your first 10 rows of data are to get a feeling for what's actually in the CSV file. And yeah, this is how you can visualize data points. So you're plotting on the x1, x2 plane, and the dots just tell us which labels we have for each coordinate. And we do see this circular decision boundary that we talked about. So something interesting happens when we use Z1 and Z2 instead to visualize our data. And like we said before, when we regress, when we use we do have a linear decision boundary that separates both classes, but we just use another way of representing the same data. So that's interesting. So I heard you use stats model last week, but I'll discuss the solution for it with scikit-learn, but there will be, we can, if you like, we can do, I'll show you the second solution as well. So we start by, we define x, so these will be the columns of the data of the pandas data frame object that we want to regress on. So yeah, so we create a new object that contains these two columns, the quadratic terms. Yeah, when you're using a library, certain libraries function, a certain library for the first time, it's a good idea to have a look at the corresponding documentation, specification. So one important thing here is you have to specify penalty. This is a term that just penalizes larger coefficient values. And if you don't set it to none, it will use the L2 norm to regularize or penalize larger beta values. Yeah, it returns a model object, and it has the attributes yeah, some attributes that you can use to yeah, so you can make queries with regards to these attributes to see what's actually in the model. Okay, so we first create this logistic regression object and fit it to the data we have at hand. So we're regressing the column y on columns z1 and z2. So can you tell me what happens in the background when I run model.fit, like mathematically, what's going on here? I just want to hear one title that was part of the recap. So how do we fit a logistic regression model? Yeah, principally maximum likelihood estimation, right?
Yeah.
Plus some iterative algorithm for optimization. That's correct. Yeah. Thank you. So that's what the function does. MLE in some iterative optimization algorithm on top of it. Okay. Like we said, this fitted model object has the coefficient underscore attribute in which you can look up which parameters you have in the final fitted model, and we have -10 approximately for beta 0, 10 for beta 1, and again approximately 10 for beta 2. And if you plot it, if you plot the data points in z1 and z2 coordinates with the decision boundary that was obtained with this logistic regression, you get exactly this. So that's what it looks like when you okay. So this is the Statimals equivalent of it. If you've done everything correctly, you should get the same coefficients, and it seems to be the case here. So again, we have roughly -10, 10, 10. And yeah, of course you can use, it makes sense to look up what our model actually outputs. For that we can use the same data points that we have in X, so Z1 and Z2 coordinates. And you can plot your predictions. So these are the predictions. You have, the model predicts just 0 within the circle and 1 outside of it. And what we see is that we do miss a couple of points, but that's expected. But it seems to be a pretty good fit, right? So this is the decision boundary that we obtained by the logistic regression, and in the background you have the actual labels. So it seems to be a pretty good fit. Yeah, and here is what we talked about along this decision boundary. The probabilities are close to 1/2 according to this color scheme, right? Okay. So remember we had -10, 10, 10, and sorry, something wrong with my. And the linear decision boundary is given by -1 over beta 0 times beta 0 plus beta 1 x1, and if you substitute values in the fitted model, you get 1 minus x, and that's exactly the decision boundary that we get here. Okay. Are there any questions? on this process?
So,
Yes.
so we fitted, we predicted the same data basically, right? There
Yes.
was no test. There
So
was
the
no
only
split.
thing was using the quadratic term instead of x1 and x2. And it's the only way to still get the linear decision boundary,
Yeah.
with which you can still reasonably fix a logistic regression model to that has this.
Yeah.
Okay. So now we're given the information. For the time, you just forget about what we did. Someone tells us with certainty, I mean, if you take this data and draw a circle like this, that has the radius 1 and has its origin as 0. Here. Someone tells us that all data points belong to class 1 with certainty, and those within the circle belong to class 0 with 98% chance. So if we just use this as our decision boundary, we'll get a pretty good model. So 100% chance for class 1 and 98% success rate.
So the red dots inside the class 0 circle are representing the 2%.
Yes, exactly. So I don't know if you can actually see it here, but okay, so here we have 3 misclassified data points from what I'm seeing. No, okay, 3 missed, and these are misclassified as well. So the idea is again, I'm not sure if you can actually see this in the plots, but this is supposed to be a better model with a decision plan boundary in terms of correctly classified data points. So this one on the left has
Yeah.
so the intended observation is that your the decision boundary that you obtain with your logistic regression may be suboptimal with regards to the number of data points that you actually correctly classify. And can someone maybe like to would someone like to explain why? I mean, the explanation is very straightforward, actually, in what I. So, what does my optimal parameter beta represent in case of logistic regression? What does it do? In what way is it optimal? I mean, it's a parameter that maximizes the likelihood, right? Not necessarily the number of data points that you correctly classify. And that's the intended takeaway from this test. That's all there is to it. Write, try to formalize this, but under heavy abuse of notation, so don't take this too seriously. one with a slash next to it, it's just a linear function. So if you have, for example, x strictly larger than 0 within these brackets, this function outputs 1. If x is actually larger than 0, then 0 otherwise. So main takeaway, logistic regression, and is optimal in terms of and that concludes exercise 1. Yeah, the third exercise in particular is very short, so I think we'll be able to finish roughly at the expected time. Okay. Are there any questions on first exercise overall? Then let's continue with exercise 2. This was discussed in the lecture in some detail. So maximal language estimation, the general process of it, and how you apply that to logistic regression. So 2 years ago there was an exercise, an exam question that asked you to perform MLE on a Poisson model, a Poisson GLM. And a lot of there were many successful solutions. Created a lot of how should I call it, frustration among the students who took it. So it would be a good exercise for you to try to perform MLE on other types of GLMs, not just logistic regression. Anyway, so the task is determine the Lagrange function. The log likelihood compute its gradient, perform one step of gradient ascent, and then we'll talk about how we'll talk about the probabilities of this particular data. Okay, so maybe can someone tell me what's the idea behind MLE? So what are we trying to maximize?
The likelihood that you observe exactly this data with the
Exactly.
model.
That's exactly how I would have told it, so and I want to hear that. So you're trying to find the primitives that maximize the likelihood that you observe your data set, your overall data set. So that's the idea. I will give you again 5 minutes to conceptually solve tasks A through C. You don't have to do the entire computation. But it'd be enough if you just came up with some solution approaches to all 3. Like just ansatzweise. I mean, even I was too lazy to learn it again and again, so it's hard to hear stuff. talk about how you do MLE or logistic regression. Yeah, to illustrate the principle, like you said, we're trying to maximize the probability that we observe these exact n data points. And how to do that is via taking, you can put them together in a big product. So that's the joint probability of your entire data set. Because we're assuming that data points are independent, their distributions are independent of each other. So that's how you formulate your likelihood function. And we have here, we just need to use the probability density function for the given type of distribution. In this case, for example, we have the Poisson distribution, and our perimeter mu is indirectly given by the inverse of your link function applied to your linear function eta of x. So you can put the mu that you formulate like this, like inverse of g applied to eta of x. You can plug that into wherever mu shows up in your PDF, and you just plug that into your likelihood function, and then you have a fully formulated likelihood function. That's the idea. Is that a video? Okay. Just make sure I don't see, because I really hate to hear my voice and it circulates.
I'm too slowly, that's why I need the time to recap.
Okay, so okay, so this was formulating the likelihood function for a Poisson GLM. I know we want to do it actually for logistic regression. And yeah, y next is regular p. Our link function is the logit function. We such that it's equal to eta of x, which is our linear model. And with that we get the mean of y and x as the inverse of log x or sigmoid applied to eta x. Or actually we don't even need to go that far, because task A just wants us to express L in terms of P sub time. And so we just need the probability density function of a binary distributed variable here. And we're done with task A. Okay, so this part comes from the fact that my condition on x is binary distributed with p. This is a probability density function for a binary distributed random variable, and the thing you see here above is the short way of writing it. Okay. Yeah, so this is the complete solution for task B. I'll just explain the steps very briefly. So this part we already did in task A. Then we can go ahead and substitute the information that's given here that relates PI to our coefficients beta and xi. And this is the fully formulated likelihood function that you get for logistic regression. And then we apply the natural logarithm. It makes things easier for computing the derivatives. So I assume you know how the logarithm works, but yeah, this is just the natural logarithm applied to the expression here above. So the yi and the exponents become factors multiplied with the natural logarithm of the basis here above. Then we want to compute its gradient, which you can efficiently do using the chain rule. Anyone who for analysis 1 should be familiar with the chain rule. I'm not going to describe it in much detail. And here on the left, here on the right hand side above is all the derivatives that you need to evaluate this derivative using chain rule. So after all these steps, you end up with this expression here for the gradient of the log likelihood with regards to beta. So we will use that in part C to compute one step of gradient ascent. So we want to maximize log likelihood, so we were using gradient ascent and not descent. So what's the general rule for one step of gradient update? We take one step alongside the gradient, evaluate it at the previous step, beta j, and weight it with some learning rate alpha. So that's the update rule. And now we want to find out what beta 1 is using this update rule. And so that's the general idea of what we're trying to do here. And this is a fully formulated solution. So here below all the necessary steps of computation. So we have our data here, and then sigma of 0 is 1/2, so we get a vector of minus 1/2, minus 1/2, 1/2, 1/2 for this. And yeah, I mean, it's just arithmetic. So using the values you have in your data set and your initial parameter value, you compute this initial derivative of the log likelihood function, which is 0 over 1.75 or 7/4. And then we can easily update the gradient using this update rule. So initial parameter vector 0, 0 plus the gradient that we computed weighted with our learning rate, and it yields this new two-dimensional vector 0 over 0.35. So hopefully if I computed everything correctly, the log likelihood evaluated at beta 1 should be larger than log likelihood evaluated at beta 0. That's the whole idea of gradient ascent. this is more or less the same set of steps that you follow regardless of the situation. So, just again, it would be a good idea to maybe do tasks, parts B and C for the Poisson model that we talked about in the beginning. So try to do maybe as an exercise for yourselves this entire process for another type of GLM, like I said before. Okay. So are there any questions on this? Yeah, the final task. So the question is, what could be the problems with regards to Gauss-Markov properties when we try to fit a linear regression model to this data? So if you do try to fit both OLS and a linear logistic regression model, just these 4 data points, which is actually nonsensical, but you get a model like this, and it looks more like this. So this is the probabilities that your logistic regression model outputs for each x, and this is your linear model. And I'd like you to take about 5 minutes to think about this. Yeah, again, these are the reminders with regards to Gauss-Markov assumptions. Just try to formulate some, like a diagnostic of this linear model here in purple. So let's talk about this already, so we have sufficient time left for the design exercise. So the first problem with such, what's the first problem? That doesn't necessarily have something to do with Gauss-Markov assumptions. When you try to fit a linear model to what we have here.
Maybe he's a risk of explicit.
Yes, we will talk about that. And why?
Because their terms depend on x.
Exactly. Very good. So were to continue this line, as we move further to the right, our labels will remain at 1 because we do have linear relationships. So the further right we move, so the larger the x values get, the likelier it is that the actual class is 1. But what do we observe? So homoscedasticity would mean we have constant variance. But what we do see here is that the error terms the magnitude of the error terms get larger as we move to both directions actually. So also here we will keep up, the true labels will remain at 0, but our predictions will keep decreasing. Does that make sense? And also, the residuals aren't even normal distributed. That was also part of the homoscedasticity assumption, right? Yeah, the residuals aren't even normally distributed. The best you can say is that they're Bernoulli distributed and not even with a fixed variance. Right? Would you agree with that? Okay, so that's one problem. Okay, so what else? So do the residuals exhibit some sort of pattern or not? Because autocorrelation usually appears, and it's one common thing that leads to autocorrelation is when you have functional specification. So there is some behavior. So if the residuals exhibit some sort of systemic behavior that your model doesn't, at that point it implies that your model itself doesn't capture that behavior, right? It was discussed in much more detail last week, I'm assuming. So indeed we have a violation of that in this case. Because, yeah, I mean, depending on where we are on the x-axis, for example, here we'll always get positive residuals, and here increasing negative residuals, increasing magnitude, right? So there is some pattern that's not explicitly modeled that's not captured by our model. So I'll just write. And like the final problem that has something to do with Gauss-Markov assumptions is you're outputting values for y that are not in your actual range, which is just 0 and 1, because we have binary labels. So range. So the intention behind this task is those Gauss-Markov assumptions are very restrictive, right? I mean, you do get an optimal perimeter with least-squares estimations when all of these conditions hold. And with generalized linear models, you are still able to express some linear relationship between your output variable and your independent variables under relaxation of these assumptions. So you can relax a lot of these assumptions and still get a reasonable decision boundary, a reasonable model. So that's the idea here. That's why we need JLMs. Okay. So final really doesn't take more than 5 minutes, but I'd like you to take, so we have a Poisson regression model, we already talked about this. Just try to formulate how the mean of your independent variable changes with regards to your independent variable age. In this case, it's age. So just take 2-3 minutes to think about this, and I'll briefly outline the solution. Question here in the first task is how does the expectation of your dependent variable changes with age? So first you want to answer that positively, which means does this mean increase or decrease with age?
Decrease.
Yeah, that's right, thank you. So the bigger we make age, so we have a negative coefficient in front of age. Yeah. So in task B, we want to answer the question quantitatively. So we want to answer, okay, decreases, but by how much? And it's also fairly easy to do. And which is the digital logarithm. So we have this relationship between the mean and linear model. So mu equals e to the power of your linear model. And we want to say how much, answer the question how much does mu change when you increase h by 1. And this is the full computation that goes with that. So we find out, you can write this new mu as the original mu times e to the power of your coefficients, your coefficient eta 1. And if you evaluate that, so if you evaluate e to the power times 0.005, you get approximately 0.195. So, which means you get a 0.5% decrease in your estimated incidence rate. When you increase h by 1. Yep. That would be all from my side. If you have any questions, I'll be in the room